Right at the end of class, we were talking about the situation that can occur when your vector is in quadrant 2 or quadrant 3. And I want to illustrate with a quick example and then summarize with a quick rule of thumb. So here it is. If my vector is in quadrant 1, let's say it is the vector 4, 3. So here's my vector A, which is 4, 3. And I wish to convert that into polar form, and so I do the usual. First I compute the magnitude, which is equal to the square root of 4 squared plus 3 squared, which turns out to be exactly 5. And then I compute the angle, remembering that the angle is going to be the inverse tangent from y over x from the inverse tangent of 3 over 4. And that turns out to be 37 degrees. So that gives me my vector A is equal to 5 at an angle of 37 degrees, and there's no problem with that. If I now go into the third quadrant, and I create the vector -4, -3, let's call that B. Like so. Then, if I try to do the same computation, I get the magnitude of B is equal to the square root of 4 squared plus 3 squared, remembering that I'm going to treat the negative components as having positive length here. And so again, I get 5. So it gives me a 5 for my magnitude. And now if I try to compute theta is equal to the inverse tangent of y over x, look what happens here. The negative signs from the -3 and the -4 cancel out, and they give me the exact same angle as I got for A. So that according to my computations, vector B and vector A are the same vector, and they clearly are not. In fact, B is the opposite of A. So what happened and how can we fix it? What happened right here where my negative signs canceled out. And they canceled out because this vector was in quadrant 3, in which case I had the 2 negatives. So, what should I do about that fact? Well, what I should do about that fact is to recognize that there is a 180-degree difference between these two vectors. They are literally the opposites of each other. Notice here how B is equal to -1 times A. And that means that it is the same vector, but in the opposite direction. And so I'm going to have to manually add 180 degrees on to get the correct angle of 217 degrees. In other words, A is an angle of 37, B is going to be at an angle of 217. Just like that. Well, a similar kind of thing happens for vectors in quadrant 4 and quadrant 2. If I have this vector here in quadrant 4, and that vector is going to be, let me erase some of this right here. This vector is now 4, -3. Let's call it C. And I now compute the magnitude of C as the square root of, again, 4 squared plus 3 squared is 5. And I compute the angle, which is the inverse tangent of y over x, or the inverse tangent of -3 over 4. The calculator is going to tell me -37 degrees, meaning that it is 37 degrees south of due east. That's not exactly standard form, but I can put it in standard form by adding 360 degrees to it. And when I do, then I get 323 degrees. That would be measuring all the way around here, 323. Okay, well that's fine. But then when I go over to quadrant 2, and I create now a vector -4 and 3, and let's call this vector D. So D is equal to -4, comma 3. And if I compute the magnitude, to nobody's great surprise, I get 5. If I compute the angle, then I try inverse tangent of y over x, which is inverse tangent of, would you look at that? It is the same value, -3/4, as we had when we computed the angle for C. And so my calculator is going to tell me -37 degrees, and that's just wrong. This isn't 37 degrees below this angle right here. It's not 37 degrees below the east. What happened? What happened was the same thing that happened with our vectors A and B. And that is that D is exactly opposite to C. And therefore, I need to add 180 degrees to its angle to get the correct angle, which is 143 degrees. Well, you say, okay, that was interesting, but how do I know when I should add 180 degrees and when I shouldn't? Well, it's actually very easy. The calculator will always gives angles in quadrants 1 and 4 only. These quadrants right here are the angles that we're going to get. In other words, between -90 degrees and positive 90 degrees, that is the range of angles that we're going to get. And actually, the calculator will never get us exactly those, so let me put parentheses on that. But if my vector happens to be in quadrants 2 and 3, just like B and D were, the calculator will not give me these angles. Instead, it's going to give me matching angles over in the other quadrant, and so that's when I have to add 180 degrees to them. What do all the vectors in these two quadrants have in common? Well, their x components are negative. That's it. And so we have now our complete rule that for any vector, except the vertical ones, theta is going to be the inverse tangent of y over x, and then we are going to add 180 degrees to our angle if x is less than 0. This will give us the right angle in all